Hi, I'm Mateusz Kamiński, the team leader of UW Crowd's team, developing a student immersion rover at the University of Warsaw. Our team has about 15 members, divided into sections: mechanics, electronics, and programming. Beside the technical structure, we also have a small administration group made up of the most involved members. To keep everyone aligned on the technical side, we hold weekly meetings. It helps the whole team see what the others are working on, share interesting updates, and stay on top of deadlines. It's worth mentioning that our team consists mostly of physics and programming students from a non-technical university, so we learn nearly everything ourselves or from one another. On board the rover, we have a 5 degree of freedom robotic arm built from aluminum profiles and DC motors. Its strong and durable construction allows it to handle relatively heavy objects, and compact DC motor drivers mounted directly on the arm enable precise control. By combining the arm with the rover's forward-backward motion, we can achieve a functional fake 6 DOF workspace, which is sufficient for the instrument deployment and maintenance operation. Our drill unit can collect subsurface soil samples from depths up to 20 cm and has been tested in both wet and dry sand. Together with our science unit, we can measure soil pH, humidity, temperature, and collect samples on board the rover or drop them at the base station with the help of the robotic arm. The system currently supports up to 3 sampling and measurement cycles, but can easily be extended to handle more. The chassis is built from aluminum profiles with plexiglass and polycarbonate side panels and bottom panels, topped with textile cover with many components mounted using Velcro. While not an optimal engineering solution, this approach makes assembly and adjustments much easier in a rapidly evolving project. The suspension system is a rocker type, with our own novel approach to creating a differential using tensioned cables. The entire mechanism was designed ourselves with the support of the Faculty of Physics Mechanical Workshop. Our wheels are currently rubber-based, but we are working on replacing them with aluminum rims combined with TPU and PET prints. The drivetrain uses e-bike motors with integrated gear reduction, one per wheel, controlled by VESC drivers. This whole setup provides high torque, good control, and strong resistance to terrain irregularities. At the center of our rover is the Jetson computer that manages all control functions. It runs ROS2 topics to provide control of the system while also handling telemetry, camera feeds, and measurement data. The PowerBoot module, along with the step-down converters, supplies power to the rover, provides emergency stop functionality, and monitors battery voltage. Communication between modules is handled via CAN bus, ensuring reliable connections. The camera system uses USB cameras that provide high-resolution imaging with suitable hardware. Long-range communication with the base station is accomplished using AirMax antennas, forming a stable link for ROS2 data. The camera, robotic arm, and drivetrain systems altogether enable the rover to perform reconnaissance and autonomous delivery operation, such as navigating the terrain, identifying objects, and executing pick-and-place tasks. We have recently begun our work on full rover autonomy, but it will not be ready for this year's IRC. For now, the rover will be manually operated with GPS reporting and possibly terrain mapping. We will keep testing our rover for the reconnaissance operation, focusing on training our operators in spatial awareness and attention to details, to practice rulebook tasks such as opening panels, plugging connectors, and operating joysticks. To evaluate the science system, we'll test the drill and measurement board on different materials with various moisture contents as we calibrate the soil sensor. Field tests in natural conditions will help us see how the system handles issues like jamming or any potential mechanical flaws. Since reactivating the project in January this year, we have made significant progress across all things, which include setting up the entire system in ROS2, developing the drill and science modules, designing a new chassis, building the suspension, and creating the powerboard unit. In preparation for the IRC, we'll present these developments during mock sessions, together with the astrobiology exposition results, the business and partnership plan, and the overall rover overview. We are very excited to show you what our rover can do at the International Rover Challenge. Thank you and goodbye.